Hey guys, back again, Chapter 2, Lesson B on polynomial functions of a higher degree. Objectives are as follows. Use leading coefficient test to determine end behavior, looking at zeros and extrema of polynomials, as well as repeated roots and finding zeros of polynomials and finding polynomials given zeros. So let's go ahead and get started. So polynomials have the following qualities. Their graphs are continuous for all real numbers, and they are smooth. Therefore, polynomials do not have the following qualities. They do not have holes or gaps, and do not have sharp corners. So here's a polynomial. It's kind of a goofy looking one. This is not a polynomial. Right, because of those sharp corners. Here's another example of a non-example of a polynomial because of that jump or gap. That's a no-go. Okay, so polynomials are continuous, which means if you're graphing it and it's you don't have to pick up your pencil or pen or stylus or whatever, and it's still a function, and it does not make any sharp turns, then you've got yourself likely a polynomial. Let's look at some other characteristics and get into some of today's lesson as well. All right, so let's look at something called the leading term test. Examining the leading term of a polynomial tells whoever's looking at it much about the polynomial's end behavior. So here in orange, I've got highlighted the leading term, right? So for example, in the red function, r of t equals 3t squared plus 6t plus 13. This is our leading term. In the green function, I've got negative 3t to the fourth. In the blue function, 7t cubed. And in the black function, negative 7t to the fifth. Now, each of those functions has a very unique situation going on with it. What we're going to do is we're going to consider both a sub n and n. So if n is even, like you see in the red and in the green function, and if n is odd, like we'll see in the blue and the black, what that means is that the degree of the polynomial is even or it's odd. The degree. Okay, so this value for n is the degree. Is it even or is it odd? So if it's even, the function is either going to, on its end behavior, on its ends, go up in both directions or down in both directions. So how we determine whether or not it goes up in both directions or down in both directions or ends is whether or not that leading term, its coefficient, is positive or negative. So you can see here that this is a positive 3. So if you have a positive, even leading term, positive leading coefficient, even degree, you're going to have this end behavior in the top left box. If you have negative even, you're going to have the bottom left box. Okay, with an odd function, I might want to do this so you can see that it goes with that function. And this for the green. If you have an odd positive, we will see down to the left, up to the right. And if we see a negative odd, we'll see up to the left, down to the right. That's called end behavior, right? There's a lot of stuff going on in between, but it's end behavior. So let's talk a little bit about zeros and relative extrema. So a polynomial of degree n can have at most n zeros, which makes sense, right? So if I had a quadratic, like the red function above, it could have at most 2 zeros. Could it have 1? Sure. Could it have 0? Yes. Okay. Now a polynomial of degree n can have at most n minus 1 relative extrema. So it can have at most 1 extrema, 1 turning point, if you will. Okay, and that works for all functions, all polynomial functions of even or odd degree, right? At most n zeros and at most n minus 1 relative extrema. So let's get into that stuff a little bit more in the slides to come. Okay, in this next slide, we're going to use the leading term test to determine the left and right end behavior of the following functions. So here I've got a negative odd. Negative odd will tell me the following: up to the left, down to the right. So I'm going to actually introduce you here to a limit notation, a notation that helps us to kind of speak mathematical language. So the limit, which is just the direction, okay, as x goes to negative infinity, right? I'm referring to this portion. As x goes to the left, what's happening to f of x? Well, what's happening to f of x is that it is headed to positive infinity. Okay, let's talk about that one more time. The limit as x goes to the left, negative infinity, headed off to the left, of f of x is infinity, so it's headed upward. If you would, pause the video and try to write the right end behavior. The limit as x goes to positive infinity of f of x is equal to negative infinity. It's going downward. Let's look at the blue function. Okay, this is an even function with a negative leading coefficient. So its end behavior would look as follows. Left end behavior, limit as x approaches negative infinity of g of x, let's put f of x, would be negative infinity. Limit as x goes to positive infinity of g of x is also negative infinity. Both are headed downward. Okay, the green function, odd, positive, down to the left, up to the right. Limit notation, limit as x goes to negative infinity of h of x going downward is negative infinity. Limit as x goes to the right or toward positive infinity of h of x would be up without bound. Okay, so let's go back to the red function for a second. Cubic function has at most 3 zeros and at most 2 extreme values. G of x has at most 10 zeros, at most 9 extreme values. Green function h of x, at most 17 zeros. That'd be pretty crazy. I would love to have to find those. Hopefully some of them are repeated like we'll see in the next slide here. And max number of extreme values of 16. Let's keep moving. Okay, so this slide isn't going to have much new for us other than a possible repeated Ruud. So we've done a lot of solving, you guys, up to this point. In chapter 1, all that I want to do is find the zeros, which means I want to know where f of x equals 0. So I'm going to factor out an x, which leaves me with x squared minus x minus 2. And then I'm going to hope I can factor. If I can't, I might have to use the quadratic formula. It looks like minus 2 and a positive 1 will work. That gives me zeros of x equals 0, x equals negative 1, x equals positive 2. So I'm going to have zeros of 0, negative 1, positive 2. So negative 1, 0, 0, 0, and 2, 0. Now, if we consider this function, it's cubic. Okay, it's cubic with a positive leading coefficient and clearly an odd power. So the end behavior would be down to the left, up to the right. The only way to make this work, since I have at most 2 relative extrema, is to pass through each of those zeros and create that function. Now, I have 3 values, right? 3x values, or x-intercepts. I don't know exactly what these values are. Okay, I don't know those. I could use my calculator to find the max value here and the min value there. I'm not concerned about that necessarily. This is a possible graph, and you could use your graphing calculator to find those, okay? So on the side, find those extreme values and get comfortable with that. I've drawn a possible graph for this one. Okay, let's look at g of x. Again, let's set this equal to 0. Let's factor out what we can. I'm going to take out a -2 and an x squared. What I have left is an x squared minus 1. So let's continue to factor this with a -2x squared. If I factor the difference of squares here, I'll be left with zeros at x equals 0, -1, and +1. Now, what I'd like you to notice is that I've got x as a 0 twice, and what happens in that scenario is that this becomes a repeated root. And a repeated root, I'm going to talk about further on the next page, that happens an even number of times. So twice in this case, we'll have the graph touch but not cross. So the general sketch of this function with x-intercepts -1, +1, and 0, as well as end behavior that would look like the following, would have to do something like that. So as you get more comfortable with looking at the leading term, its leading coefficient, and the degree, as well as repeated roots, you'll get into what's called curve sketching, which we're going to do a little bit here throughout the rest of the notes. So let's go ahead and jump into the next slide. All right, so repeated zeros or repeated roots, those two are synonyms. For a polynomial function, a factor of x minus a to the k power with k greater than 0 yields a 0 of x equals a with multiplicity k. Okay, that's a mouthful, okay? But if k is odd, the graph will cross the x-axis. If k is even, the graph will touch but not cross, like we saw in the last example. So let's sketch a possible graph of each of the functions below using your knowledge of end behavior and repeated roots. So where would my x-intercepts be for f of x? They would be at x equals -5, -3, and 2. What would my end behavior look like here? Well, I've got a negative value, which would be on the leading term. And notice I've got a 2 here, a 1 here, and a 3 here. What that tells me is that my leading term for f of x, I don't really care about the rest of them necessarily, but my leading term would be a negative x to the 6th power. What you do is you add up 3 and 1 and 2. Okay? So if I know that I will have a leading term of negative x to the 6th, I know my end behavior on both sides will go downward toward negative infinity. Let's sketch a possible curve for this. Here's the point -5, 0. Here is the point -3, 0. Here is the point 2, 0. So let's analyze the behavior. Notice that at x equals 2, I've got an even degree. Okay, that's a repeated root. twice. So I know my function is going to bounce off there. Okay, let's first sketch our end behavior. Okay, here's what my end behavior is going to look like. I know my graph has to bounce off of 2. That means it won't pass through. That means it'll do something to this effect. All right, since -3, or the factor x minus 3, has an odd power, and so does -5, the function or the graph will pass through. Okay, so it's going to pass through -5, pass through -3, come back up and touch and bounce off. Okay, now I don't know anything about these local extrema. That's going to have to be calculated on the graphing calculator. I do know one relative extrema right here. That's a relative max, but that's how you curve sketch. You first develop the end behavior, your roots, and then your behavior at those roots. Does it pass through, or does it touch and bounce off? Let's do the next one. The next one, I want you to be very careful. Okay, let's look at the zeros, also known as the roots. I've got a +4, I've got a -3, and I've got a -3/2. Okay, so leading term. Okay, you want to be careful here, but I do know that I'll have an x to the first, I'll have an x to the second, and I'll have an x to the third. Okay. Now, speaking of leading term, okay, think about what will happen if I were to FOIL out that expression. Well, would you get a +x² or a -x²? And since you're squaring it, you would get a +x². Okay, in the next term, you would get a +x². In the last term, you get a 2x. So if you had an x² times an x² times a 2x, you'd have 2x to the 5th. Now, if I also included the 7, my leading term for g of x would be 14x to the 5th. So I know end behavior-wise, odd positive is going to look like that. So let's quick put our zeros down. Here's -3/2, 0. Here is -3, 0. Where's -3, 0? How about here? There it is. And then I've got 4, 0. I've got even roots or repeated roots at 4 and at -3. I've got end behavior that's going to look something like this. Okay, so I've got an even root. I'm going to have a bounce or a touch and go, if you will, here. I'm going to have a touch and go there. Not my best sketch, but that's okay. And then I'm going to have the function pass through and come back down. So clearly I can identify a couple of these extrema just based on the fact that they're even repeated roots, but I can't find necessarily without a calculator those relative extrema. Now, one thing I do want to point out is that I could find the y-intercept if I plug in a 0 for x. So let's quick do that. If you plug in a 0 for x, so g of 0 will be 7 times 4 minus 0 squared times 0 plus 3 squared times 2 times 0 plus 3 to the first. So, boy, that's going to come out to be, gross. 7 times 16 times 9 times 3 times 27. I don't know what that comes out to be, but it's going to be a big number, right? So it's 7 and then that number, whatever that is. So clearly not going to fit on my graph based on the scale that I've drawn. Okay, let's move on. We got 2 more slides left. All right, in these examples, I want to find a polynomial of which there are many possible answers with the following zeros, okay? So if x equals -1/2 is a 0, then if I added the 1/2 over, then this is a factor. Okay, now I'm going to write it in a slightly different way just to make the absence of fractions nicer for us, okay? And I see that I have a repeated root at 3. That means I'm going to have x minus 3 twice. So p of x is equal to 2x plus 1 times x minus 3 squared. Notice how the sign of the 0 in the 1/2 case is negative, but when I write it as a factor, it's positive. And 3 is positive, and in here I've got a negative, right? It's just the value that makes the factor equal to 0. Okay, so q of x, this one's slightly more difficult. I can definitely work with this. But if I were to shortcut and not go the way I did over here and write out the 0, then the root, I could write x minus 3. Now I've got x plus, or excuse me, 2 plus root 11 and 2 minus root 11. So I'm going to do x minus 2 plus root 11 and x plus 2 plus root 11. And then my last factor is x minus 0. So I'm going to regroup this just a tiny bit. Put the x alone, which was from this x minus 0. Then x minus 3. And what I'm going to do in just a moment here is I'm going to FOIL the last part. I could leave it like this. I don't know. Maybe I will. We'll see. Root 11. Okay, I might leave it in factored form. Actually, I'm going to go just one step further just with this part. I'm going to clean this up and leave this in this form. Now, the question on a test or on a quiz or anything like that would specify a little bit further, but I'm going to go ahead and FOIL this out. That would be x squared minus x times 2 plus root 11 plus, oops, I'm sorry, that should be plus x times 2 plus root 11 plus x times 2 minus root 11. Okay, and then I'm running out of space here, but then negative 2 plus root 11 times 2 plus root 11. Okay, so everything that came out of that was this. Alright, so let's try to combine some like terms. So q of x. The only reason I'm doing this is because I don't like the roots in there, so it's kind of preferential, but whatever, we'll deal with it. So I'll have x squared. Okay, notice I'd have 2x and 2x, which would be plus 4x. And then if I were to distribute here, these would cancel, right? I'd get x root 11 and negative x root 11. So we're good there. But now we have to FOIL this thing. Okay, so let's go minus. That would be 4 plus 4 root 11 plus 11. This is a yucky one. Okay. Oops, I'm sorry. Oops, I messed something up there. My bad. This right here should actually be a minus. Alright, I didn't want those radicals in there. I knew something was wrong. So I'd have plus 2 root 11 minus 2 root 11. So those would go away. And then I would have minus 11, right? Because root 11 times 11, root 11 is 11. Okay, that's getting really messy. But Here we go. Let's finish this up. Probably shouldn't have put this example in here, but that's okay. You're getting some algebra in. You would have x squared plus 4x minus a negative 7, which would be plus 7. All right, there you have it. There's p of x and q of x, writing a polynomial with the following zeros. So let's see what we got on the last slide here. I just looked and we got nothing on the last slide. Okay, guys, that's it for today's lesson. That is, I believe, 2b on higher powered or higher degree polynomials. Let me know if you got any questions. Have a great day.